Mathematical methods. So we are having three types of methods. First one is mechanical translational system. Mechanical translational system. And second one is mechanical rotational systems. Mechanical rotational systems. And the third one is electrical systems. So here we are having three parameters in each method. First one is in the mechanical translational system, we are representing the system with three parameters. First one is the mass, dashpot and spring. And here same moment of inertia, dashpot and spring constant K. So here in this case mechanical translation system, input will be force applied on the body and the output will be displacement existing by that body with the applied force, displacement. Here the input is torque applied on the body and output will be angular displacement. So whereas after representing with this mechanical translational system and mechanical rotational system, we need to match with electrical systems. That means we need to find the electrical analogous parameter which are existing in translational and as well as rotational systems. So here also, as we discussed in mechanical translational and rotational systems, we are having elements such as resistor, inductor and capacitor. So here input may be voltage source or current source. So the output may be work done or charge in the circuit. So after finding with mechanical translational system and rotational system, we need to match with electrical systems. So this topic represents mathematical models in mechanical translational system, mechanical rotational system, and after that we are comparing these two systems with respect to electrical systems. So let us see first mechanical translational system. Mechanical translational system. So in the mathematical models of mechanical translational system, it can be obtained by three basic elements as we discussed just now. First one is the mass represented with capital M, and second one is dashpot represented with in some textbooks B, in some textbooks D, and spring constant K. So here the weight of the mechanical translational system is represented by M, mass M. So this entire weight of the body is represented with mass M, and it is assumed to occur only at the center of the body. It is assumed to occur at the center of the body. And the elasticity of the mechanical translational system can be represented with spring constant. Elasticity represented with spring constant. And the friction existing in the mechanical system can be represented by dashpot. Friction existing in the system can be represented by dashpot. Elasticity existing in the system can be represented by spring. and where B or D, so I am representing with B entire notation. The B is nothing but it is a piston moving inside a viscous fluid. It is a piston, this is a piston moving inside a viscous fluid. So this is my dashpot. So this is the piston moving inside the viscous fluid that can be represented by using dashpot B. So here in this analysis we need to understand the Newton's second law. By Newton's second law, the sum of applied forces is equal to the sum of opposing forces on the body. So this is a important law we are applying in mathematical methods. Sum of applied forces on the body is equal to sum of opposing forces by the body. So sum of applied forces on the body is equal to sum of opposing forces by the body. Sum of opposing forces by the body. So this is the law we are using in this representation. So before going to that, we will see what are the list of symbols existing in the representation. So first one is X is nothing but displacement represented in meters, and V is nothing but differentiation of the displacement is nothing but velocity. Differentiation of displacement is nothing but velocity. So meter per second. And if you are differentiating this velocity, then we will be getting acceleration, or double differentiation of the displacement is nothing but acceleration. The unit is meter per second square. And if you are applying the force which is in Newton's applied force, and forces opposed by each and every parameter in the mathematical model. So force opposing, so I write opposing force offered by mass m, offered by mass of the body, can be represented by using F of m, and you can expect now F of B is nothing but opposing force offered by the dashpot, and F of K is nothing but opposing force offered by the spring constant. And similarly, M is the mass of the body in kgs, and B is the viscous friction coefficient, viscous friction coefficients in Newton second per meter, and K is the stiffness of the spring, in Newton per meter. So these are the list of symbols which are useful in analyzing these mathematical models. X is the displacement in meters, V is the velocity in meter per second, and A is the acceleration meter per second square, F is the applied force in newtons, F of m is the opposing force offered by the mass of the body, F of B is the opposing force offered by the dashpot, F of K is the opposing force offered by the spring constant, and the entire mass of the body m is nothing but represented in kgs, B is the viscous friction coefficient in Newton second per meter, and K is the stiffness of the spring which is represented in Newton per meter. So as per the Newton's law, applied force F should be equal to all the forces opposing, that means opposing by mass m, dashpot B, and spring constant K. So this formula we are applying in analysis purpose, in analyzing the equations. So we will discuss each and every part separately. first one is the mass. So represented with capital M, and the body is represented like this. This is a mass M fixed here, result fixed here, and this is reference. If a force F is applied on the body, then it undergoes certain displacement. Let me say it as x1, right? So here consider an ideal mass having negligible friction and negligible spring constant. When we are referring only an ideal mass, these two are neglected. When we are representing an ideal dashpot, these two are neglected. Mass and spring constants are neglected. Similarly, when we are representing spring constant K, these two are neglected. So in case of ideal conditions, so I am just considering in ideal mass here, and consider an ideal mass having negligible friction and as well as negligible elasticity. Then when a force F is applied on the body, then it undergoes a displacement or distance x, then applied force is F directly proportional to acceleration of the body. So here I can take applied force is nothing but opposing force by the body. So therefore opposing force is directly proportional to acceleration of the body A. So therefore I can write F of M is equal to M into A. To avoid this proportionality constant, I am putting M. We know that A is nothing but acceleration, which can be written as M into A is nothing but double differentiation of displacement. So whenever there is a mass M, then the force offered by the mass M can be written as F of M is nothing but M into d square x by dt square, d square x by dt square. Now let us go for dashpot. Second one is dashpot. So here also I am considering an ideal dashpot such that mass of the dashpot and spring constant are neglected. So these two are neglected. So this is my symbol of the dashpot. It is nothing but piston moving inside the viscous fluid. So this is the dashpot. Fix it to one end. When a force F is applied on the dashpot, it will go certain displacement. So here the applied force is equal to opposing force by the dashpot Fb, and this Fb is directly proportional to its velocity, and we know that velocity is nothing but differentiation of displacement. So the force which is opposing by the dashpot can be written as F of b is equal to b into dx by dt. So in the problems, when we are solving the problem, we may be experiencing this type of scenario. So one side of the dashpot will have one displacement, another side of the dashpot will have another displacement x2. So both the sides it will be having displacements. If it is having one displacement like this in the above case, I can write F of b is equal to b into dx by dt. Whereas when we are having two displacements on either sides of the dashpot, then I can write, if I am representing with respect to, I can write here node 1, node 2. With respect to node 1, I can write F of b is equal to b into d by dt of x1 minus x2. With respect to node 2, I can write F of b is equal to b into d by dt of x2 minus x1. So these are the two important conditions that you have to remember when solving the problems. So these two equations are very important. Similarly, third one is a spring constant. Spring constant. K. So as we are considering in the previous cases, having negligible mass and negligible friction. Okay, so consider an idealized spring of negligible elasticity and negligible mass, negligible friction and negligible mass. This is a spring constant K represented like this. And when a force F is applied on the spring, it undergoes a displacement x1. As we know, as per the Newton's law, applied force is equal to opposing force by the spring constant K, and F of K is directly proportional to its displacement. So to avoid this, I am writing displacement K into X, equation number 4. Similarly, in the case of dashpot, we are also experiencing either side of displacement. In some cases, let us take this is x1 and this is x2, and this is node 1 and this is node 2. So here when we are writing equation with respect to node 1, it can be written as K into x1 minus x2. With respect to node 2, it can be written as K into x2 minus x1. So these are the properties of mathematical methods in mechanical translational systems.